All right, this is the video for the similar triangles topic. First, as always, open up the lesson, read through it, and have it in the background as you do the example problem, as you do the practice problems. It will be a good thing to be able to reference. You'll see if you look at the lesson here, it's focused mostly on something called the angle-angle criterion. And let's just read it, and then I'll explain exactly what it is. It says, in this lesson, we will look at the angle-angle, or just AA for short, angle-angle criterion for similar triangles, and why only two pairs of corresponding angles must be congruent in a triangle to know the triangles are similar. So if you have two pairs of angles in two triangles that match up, then you have two triangles that are mathematically similar. You know, and this is the first sentence it says here, that similar figures have all pairs of their corresponding angles congruent and the pairs of corresponding sides are proportional. Well, this says that all the pairs of corresponding angles are congruent, but you only need two of them. Triangles have three angles. Why don't you need all three angles? And it's very, very simple, because all the angles in any triangle add up to 180 degrees. So as soon as you match up two of the angles in each of the triangles, the third angle has to be the same. So if I say that you have a triangle ABC and the measure of angle A is 50 and the measure of angle B is 40, well, 50 plus 40 is 90, which means that other angle has to be 90 no matter what. So if angle A is 50 and angle B is 40, angle C has to be 90. So if triangle ABC has angle 50 and 40, and triangle XYZ has an angle that's 50 and 40, both of them are going to have a 90-degree angle that will match up, and that will be the third pair. So we're going to look at plenty of examples of that. Let's go into the very first problem. It says, given that VWX and XYZ are isosceles. Please remember that isosceles means that it has at least two congruent sides. And that's what these little tick marks mean. This little tick mark on the side WV and this little tick mark on the side WX indicate that WV and WX are congruent. They're the same length. Then the double tick mark and this double tick mark are there to indicate that this side, XY, and this side, YZ, they are congruent, that they match up. Now, why did it use double tick marks for these ones and only single tick marks for these ones? Well, the single tick mark was already used, and it didn't want you to think that side XY was also the same size as side WX. Those are very different sizes. So it uses one set of tick marks to let you know that these two sides are congruent, and then a double set of tick marks to let you know that these two sides are congruent. And an isosceles triangle has one set of sides that are congruent, at least one set of sides that are congruent. So triangle VWX is an isosceles triangle, and triangle XYZ is an isosceles triangle. So with angle WXV congruent to angle YZX. So what angle is that? Why is it three letters? When they tell you three letters, start at the first letter, go to the second one, then the third one. You'll see a little apex on the middle letter, and that's the angle they're talking about. So when it says WXV, if I start at W, I go to X, and then V, what angle did I just create? It's this angle down here in the light purple triangle, WXV, and it's that angle right there. So that is congruent to YZX, Y to Z to X. So that is this angle right here. So those two angles are congruent, this angle and this angle. So that is one pair of angles that's congruent. The angle YXV corresponds to YZX. They're congruent angles. They correspond to each other. So that's one of the two angles, or one of the two pairs of angles that we need to show are congruent. Well, it says determine how the triangles can be shown to be similar. We need the other angle to know they're similar. And how do we do that? It's pretty simple. Take a look at this drawing that I made. Here's an isosceles triangle. A property of isosceles triangles is this. If you have isosceles triangles, the angles that are opposite of the congruent sides have to be congruent to each other. So whatever the measure of this angle over here has to be the exact same thing, no matter what it is. So if you tell me that this is a 40-degree angle, then this also has to be 40-degree angle. If you tell me this is 60, this also has to be 60. No matter what this angle is, this angle has to be the same thing, and vice versa. It's the angles that are opposite of the congruent sides. They have to be congruent to each other. So if I were to finish drawing that diagram that we just saw with another smaller triangle right next to it, then it would look something like this. And then I will mark that this smaller triangle has congruent sides. And I'll even put the labels on that our original diagram did. It had V down here, W, and this was point X, and this is point Y, and this is point Z. So the very first thing it said is that the angle WXV is congruent to the angle YZX. That's this right here. So that angle and that angle are congruent to each other, but this is another isosceles triangle, and the opposite angles are congruent. So that has to be equal to the other angles also. So now we have our two pairs. These two angles are congruent to each other, and then these two angles are congruent to each other. And as a matter of fact, all four angles are congruent to each other. But what's important is that we found two pairs. And as soon as we find two pairs that are congruent to each other, it's given that the last one has to be congruent to the last from the other triangle, and then you have all three angles are congruent, and you have similar triangles. So now we go back to our problem and we see which one of the statements follows the logic that we just used. A says, since WXV is congruent, by the way, that's what that weird little symbol is, that little equal sign with the squiggly thing above it, that's the congruent to symbol. So when you see that, you read it as is congruent to. This says angle, that is a little angle symbol. So when you see that symbol, you read it as angle. Angle WXV is congruent to angle YZX. And YX equals YZ. Well, what's that? There's no angle symbols or anything in there. Usually, if you just see two letters like that, they're talking about the length of the side. Do we care about the length of the side if we're going to do the angle theorem? No, but that's not the only way that you know that two triangles are similar to each other. There are other theorems, but did we have anything to do with the two sides or anything like that being proportional to each other? No, we didn't. So we're not going to follow A because we're not talking about sides right now. We're talking about the angle theorem and the fact that we knew that we have two pairs of congruent angles. So it's not going to be A. B, since angle WXV is congruent to angle YZX, and by the way, they told us that WXV is congruent to YZX. So we know that part's true. The second part says, and angle WVX, well, hold on, what's WVX? WVX, so that angle in the bottom left-hand corner there, is congruent to angle YXZ, which is the bottom left angle of this other triangle. And that is the other pair of angles we said is congruent. The triangles are similar by angle. So that is the right answer, B. Let's move on to another one. Number 2, given that line segment DE is parallel to line segment AB, determine how triangles DEC and ABC can be shown to be similar. So something interesting about these, they both have angle C in them. We have triangle ABC, which is used as the vertex at C, and we have triangle DEC, which again uses the vertex at C. And there's only one angle at C. So they share that angle. So that angle in one triangle is equal to itself. That's the reflexive property, they call it. And since that angle belongs in both triangles, that is the first of the two angles that we need to show that the two triangles are similar. That angle right there belonging to both triangles, belonging to itself in measurement, is the first pair of angles all within itself. Now I'm going to take this and draw these two triangles individually so you can see that a little bit better, but that's a very common diagram that you're going to have to get used to. When one triangle is within another triangle, oftentimes they share an angle. And to prove that those two triangles are similar, you'll have to point out that because they share an angle, that is one pair of angles in each triangle that is congruent, the angle that they share. So what I've done here is I've redrawn the diagram just so we can see it a little bit more clearly. Now, angle C right here is in both triangles. So we have this angle from triangle DEC and this angle from triangle ABC that match up because they're both the same angle. They're both angle C, so they're obviously both the same measure. Now, we have to match up one other pairs of angles, either B to E or A to D. How do we know that either B is congruent to E or that A is congruent to D? Let's go back to our diagram with the parallel lines. And this is something that you're going to have to get used to. If you have a set of parallel lines and another line that crosses them both, or touches them both in this case, that other line is called a transversal. Now, you're going to hear that word a lot. When we're talking about parallel lines, the transversal is the line that touches both of those parallel lines. And when that happens, you get something called corresponding angles that are congruent. In other words, this angle right here, what we're calling angle B, is congruent to this angle right here, which is angle E. Their positions correspond to each other in relation to the parallel line and the transversal. When you see those two angles, they are always going to be congruent to each other as long as those two lines are parallel. Similarly, what we're calling angle A is congruent to what we're calling angle D. So that is just a law of parallel lines that you're going to get used to, and you're going to see it a lot moving forward. So because of those parallel lines, we could say that angle B, or angle ABC, if you will, is congruent to angle DEC. And since angle C is congruent to itself, those are two pairs of corresponding angles. Or we can use angle BAD and angle EDC. We can say that those are congruent to each other as well. So let's go back to the problem and read these sentences. Since angle DCE, okay, let's find DCE, DCE. Okay, that's angle C. Since angle DCE is congruent to angle ACB, well, where's ACB? ACB, yeah, that's angle C again. So obviously it's congruent to itself. And angle DEC, that's this one, what I was calling angle E in my diagram, DEC, is congruent to BAC. Is this angle up here congruent to BAC, this angle down here? No, this angle, DEC, is congruent to this angle, ABC. So A is wrong because it switched up the angle to be BAC down here, and angle DEC up here is not congruent to angle BAC down here. So A is wrong. So B starts the exact same way with DCE congruent to ACB. We already know that part's true. And the next one says that DEC is congruent to ABC, which is what we wanted. The triangles are similar by angle. That is the right answer. Now, you might have been fooled by some other ones down here. You got to be careful. You don't know anything about the sides. You have to prove that they're proportional side lengths if you're going to use the angle side theorem. So careful with those. All right, next problem. Number 3, given that line AB is parallel to line DE, determine how triangle ABC and triangle EDC can be shown to be similar. So what are the similar attributes that we can find in these ones? Again, it's best to try and look for two angles that you can prove that are the same. And here's the first one. Anytime that two lines cross, the angles that are opposite of each other are congruent. They're called vertical angles. So triangle ABC and triangle EDC have two lines that cross and make angles that are a part of those two triangles. So that angle right there, angle ECD, is congruent to angle ACB. Here's a drawing so you can see what I'm talking about. Similar diagram. When two lines cross, the angles that are opposite of each other are called vertical angles, and vertical angles are always congruent. So you've got this angle right here, ACB, and you've got this angle right here, DCE, and those two angles are congruent to each other. So that's the first pair of angles that we need to prove that these two triangles are similar. So again, that's anytime any two lines cross, anywhere. You got two lines that cross, bam, two lines cross. This angle right here is congruent to this one right here, and this angle right here is congruent to this one right here. That's always true no matter what, as long as there's two straight lines across each other. So that's the first set of angles that are congruent. What's next? Well, you have parallel lines. And just like with the last set of parallel lines that we had on the last problem, there is another thing that you can tell when you have parallel lines. And here it is. I'm going to draw a diagram of parallel lines, and I'll show it to you. And I'm going to show you all the sets of angles that are congruent when those angles are crossed by a transversal. Check out this diagram. Here we have two parallel lines. Let's just call this line X and line Y. If I tell you that line X and line Y are parallel, and then this other line, I'll call it line N, and line N crosses them both, line N is the transversal. There's that word again, transversal. The transversal that crosses this set of parallel lines is line N. All these small angles that are created are all equal to each other. Just like we mentioned a second ago, anytime two lines cross, the vertical angles are congruent, and that happens twice. And on the last problem, I told you about angles that correspond to each other. And if you take a look at this angle here and this angle here, those correspond to each other as far as having one transversal cross a set of parallel lines. So these two angles are going to be congruent. And since those two angles are congruent to these two angles, all four of those angles are congruent to each other. Well, there's four more angles on here that are congruent, but they're a different measure. So these larger angles, whatever the measure of that angle, this angle over here is the same. And similarly, this one is the same as this one. And so those 8 angles are the same. That's a little messy looking. So I'll just say that this angle, this angle, this angle, and this angle, those 4 angles all measure the same. And then this angle, this angle, this angle, and this angle all measure the same. So you have 8 angles there, but only 2 angle measures. You have 4 pairs of congruent angles. Now, if I apply that to our diagram up here, what angles are congruent? It's this one right here and this one right here. So you have this line that cuts through line AB and line DE. Remember, line AB is parallel to line DE, and line BD is the transversal. So you've got this angle here and this angle here, which in this diagram would be this one and this one. Okay. Now, those are called alternate interior angles. You don't have to really worry about what they're called right now. You'll learn a little bit more about it later, but just know that those 2 angles are congruent to each other. And that's your second set of angles that are equal to each other. There's actually a third set, and it's the same thing. You have a transversal here in line AE that cuts the parallel lines as well, so a second transversal, and that would prove eventually that this angle here is congruent to this angle here for the same reason. It's a alternate interior angle. It's just like how this angle, ABC, is congruent to this angle, EDC. So now let's go back to our problem and look at the statements that we have to choose from. We have a lot to choose from here. We can choose more than one. So let's go through these one at a time. First thing, since angle ABC is congruent to angle EDC, let's look that up. ABC is congruent to EDC. That is what we just determined through alternate interior angles. So that's true. And AC is congruent to BC. Is AC congruent to BC? And if they are, aren't AC and BC on the same triangle? It doesn't even mention a side of the other triangle. So why would that help us? So this is not true. Okay, you definitely have to relate together aside from one triangle and another if you're actually going to try and do that. So the first statement is false. We're not going to select that. Second statement, ABC is congruent to DEC. Well, let's try that one. ABC, but then DEC, this one up here, did we decide that those two were going to be congruent to each other? No, if we look back at our diagram, we did did not mark those as having the same measure. This one has 2 little dash marks. This one has 3. They are not the same. So right away, that one's wrong, and I don't want to select that option. Next one, ABC is congruent to angle EDC. That's true. That's the same thing that we started with in the first statement. That part is true. ABC is congruent to EDC. So this angle here is congruent to this angle here. That part's true. And angle ACB is congruent to angle ECD. That's also true. That's the vertical angles that we saw right in the very, very beginning. ACB is congruent to ECD. So the triangles are similar by the angle criterion. That part is true. Next statement. Since angle ACB is congruent to angle ECD and BAC is congruent to DEC, the triangles are similar by the angle theorem. So it says ACB and ECD, which we just decided was true from the last statement, but it also says BAC and DEC. Let's check that out. BAC, so that's this angle right here. Is that congruent to DEC? DEC, this angle right here. So is this angle congruent to this angle? And yes, if we go back and look at our diagram that we drew on, those ones both have 3 tick marks. Those are alternate interior angles as well. So yes, those are also congruent. If they are, then you have the angle criterion. All right. Next one, since CD is congruent to CE, okay, is CD congruent to CE? We have nothing that says that. And again, you're relating one side of a triangle to another side of itself. That doesn't help us at all. And BAC is congruent to DEC. The triangles are similar by angle side criterion. No, that doesn't work. That doesn't make sense. There's no way that you can do this problem by relating one side of a triangle to itself and not mentioning the sides of the other triangle. So that's wrong. And then finally, since ABC is congruent to EDC, which we did find, ABC is congruent to EDC. That's from what we said earlier. And BAC is congruent to DEC. That's another thing that we found earlier. BAC is congruent to DEC. The triangles are similar by the angle criterion. So basically, we found that all 3 sets of angles are congruent to each other. So any combination of the 2 of them will get you to the angle theorem. And those are the 3 statements that we chose. Number 4, triangle D was dilated and reflected to create triangle E. Triangle D was dilated and translated to create triangle F. Since both transformations included dilation, triangles D, E, and F are all similar. Which inference can be made about similar triangles? A. In similar triangles, the side lengths of the image are always 2/3 times the side lengths of the pre-image. No, that's only if the factor was 2/3, and that's not what happened here. You had 2 different dilations, so you have 2 different sets of sides, so that is wrong. If you have similar triangles, you can have all sorts of multiples that one side length can be of the pre-image. There's no restrictions on it. It does not have to be 2/3. You can see right here that 4 times 2/3 makes 6, so that doesn't work. It starts with triangle D, so if you go from triangle D to triangle F, 6 times 2/3 is not 9, so that is false. B, similar triangles have congruent sides. No. Congruent means exactly the same. If these are all similar triangles, their sides aren't the same. They're not exactly the same size. That would make them congruent triangles, so that's wrong. C, similar triangles have congruent angles. Bingo. All 3 of these triangles, all the same measures. Look, 27 degrees, 27 degrees, 27 degrees. 129 degrees, 129 degrees, 129 degrees. 24 degrees, 24 degrees, 24 degrees. That's the answer. Finally, in similar triangles, the side lengths of the image are always 3/2 times blah, blah. That's wrong just for the same reason that A was wrong. They can be all sorts of different sizes based on the scale factor of which they were dilated. Number 5, triangle ABC was dilated and rotated to create similar triangle DEF. Triangle ABC and triangle GHI are not similar. It's telling you they're not. Which inference can be made about similar triangles? A, similar triangles have at least 2 congruent sides. No, they don't have to have any congruent sides. As a matter of fact, they shouldn't have any congruent sides. If you have one triangle and you make it a similar triangle by dilating it, then all the sides will get smaller or larger. So unless one of the smaller sides just happens to get larger and become the same size as one of the larger sides of the earlier triangle that's a different size, but you're getting too far into the weeds there. The long story is they do not have to have congruent sides. As a matter of fact, they probably will not have any sides that are congruent to each other. So that's wrong. B, similar triangles have three congruents. Again, you don't have any congruent sides in similar triangles, especially not three. So that's all wrong. C, all triangles with at least two congruent angles are similar. Bingo. This is the angle criterion that we just talked about in the previous problems. If you have two angles that are similar, that means the third set of angles is if you have two pairs of angles that are congruent, that means the third pair of angles is also congruent. So that means all the angles are congruent and you have similar triangles. What does D say must be nonsense? All triangles with at least one congruent angle are similar. No, just because they have one angle that matches up doesn't mean that the other two also match up. So that is wrong. Number 6, which triangle is similar to the triangle above? Okay, so we're looking for a triangle that has 72 and 58. That's all we need, right? Angle criterion. Okay, well, 7250, 7220, 3644, and 3622. What happened? Did Study Island mess up? Did they give us 4 triangles that don't work? No. What we have to do is figure out what the third angle is. I mentioned this before, you'd better learn it, you better know it, but all triangles have 3 angles that add up to 180 degrees. If you take all the 3 angles in a triangle, they have to add up to 180. So if I'm adding 58 to 72, if I go 58 plus 72, I get 130. Well, this other angle has to get me to 180. So what does it have to be? If we have 130 so far, what's left? And the answer is 50. So the 3 angles of this triangle are 72, 58, and 50. You don't know. You can just subtract 180 minus 130 gets you your 50. Okay? Oops, I said 13 instead of 130. Try it again. 180 minus 130 will get you to your 150. Or just 50. So what we're going to do is we're going to find a triangle that has 2 of those 3 measurements, 72, 58, and 50. And which of these triangles has 2 of those? W has a 72 and a 50. So 72 and 50 will match up with the 72 and 50 of this triangle, which means they are similar by the angle criterion. 72, 50, get 2 angle pairs that match up. You are money. Next one. Number 7, determine how triangles XYZ and XWV can be shown to be similar. Well, right off the bat, you've got 2 lines that cross each other. Those are vertical angles. You're going to have to get used to seeing that. It happens a lot of the time when you have 2 angles that are vertical angles. That means they're congruent to each other. So this angle right here, WXV, and the other angle on the vertical side of that, YXZ, those are congruent to each other. So this angle and this angle are congruent because those are 2 lines that cross each other, and the opposite angles are vertical angles and they are congruent. What other angles are congruent to each other? Well, what does that little box mean? That means it's a right angle. Well, what does that mean? It means it measures 90 degrees. Well, this one also is a right angle that measures 90 degrees. So they're congruent to each other. Right angles are congruent to each other all the time. That means they both have the same measure. So there are your 2 angles. You've got the angles that are vertical angles, and you've got the angles that are right angles. So which one says that these 2 vertical angles are congruent and that these 2 right angles are congruent? So these 2 triangles are similar by angle. Let's find that. A, since XYZ, angle XYZ, is congruent to angle XWV. Well, let's find angle XYZ, XYZ, so XYZ, that's one of our right angles, is congruent to angle XWV, okay, XWV, those are both right angles, right? XWV is right here, XYZ is right here, those are 2 right angles, so they are congruent, and angle WVX, okay, WVX, that's this angle over in the corner. Is that the one that we wanted? Were we going to deal with that? No, we weren't. This is probably not going to work out well. Is congruent to ZXY, and then ZXY is this one up here. Are those 2 angles congruent to each other? No, not necessarily. So A is wrong. B, starts off the same as A does, so we know the right angles are congruent to each other. That's angle XYZ and angle XWV. And angle VXW, VXW, that's one of the ones we want, is congruent to ZXY, ZXY, that's another one we wanted, good. The triangles are similar by angle, angle. That's it, that's what we wanted. Let's do another. Given that line MN is parallel to line JK, determine how triangles MNO and JKL can be shown to be similar. So again, you've got some parallel lines and you have a line crossing them. We call that a transversal. So MN and JK are parallel. MN is up here, JK is down here. We see right away that these are marked with right angles. So those are congruent to each other. What other angles can we find? Go ahead and look through the statements. Let's go with A. Since angle MNO is congruent to angle JKL and JK is equal to MN, the triangles are similar by angle side. What is angle MNO? MNO is this one right here, is congruent to angle JKL. That's this one right here. Those are the right angles, so those are congruent. So far, so good. And JK equals MN? Is JK equal to MN? And if we're looking for similar triangles, are we trying to say that two sides are the same length? No, that's not what we're trying to do when we're looking for similar triangles. We would need to show that all the sides are in proportion to each other. Definitely not they're equal. So A is not what we want. Next, B says, since angle MNO is congruent to angle JKL and LK is equal to NO, again, trying to say that two sides are equal to each other is not going to help. We don't even need to refer to the diagram for this. We don't need equal sides to prove similar triangles. C, since angle MNO is congruent to JKL, and again, those are the right angles, so we're good, and MON is congruent to KJL. Let's look for that one. MON is M to O to N, that's this one right here, is congruent to KJL. KJL, is that one over here? KJL? Congruent to this angle right here? No way. I mean, they don't even look similar. This one's much larger than this little tiny skinny one over here. So the only answer left is D, and that had better be the answer. Let's take a look at it. MNO is congruent to JKL, that part we got, and MON is congruent to JLK. So MON, M to O to N, is congruent to JLK. Those ones are the ones we want. And yeah, D is the answer. Number 9. Which situations describe similar but not congruent triangles? So similar but not congruent. First statement, triangle PQR is dilated about the origin by a scale factor of 1/2 and reflected across the y-axis to create triangle P prime, Q prime, R prime. Anytime you do a dilation and any other transformations, you get similar triangles. So this is definitely going to work. You dilate something by a scale of 1/2. That's making it smaller. That's fine. Then it doesn't matter if you reflect it, translate it, rotate it, or anything else. You get a similar triangle. Next one. The three angles of triangle GHI have the same measures as the three angles of triangle QRS. And the side lengths of triangle GHI are twice the corresponding side lengths of triangle QRS. So the first thing is, are all the angles the same? Yes, the three angles of this triangle are the same measures of the other triangle. So that part's good, but we don't want them to be congruent. So the sides cannot be the same size. And that is what's taken care of in the second part of the sentence. It says that the side lengths of the first triangle, triangle GHI, are twice the corresponding side lengths of triangle QRS. So they have different side lengths and they're all twice as large. They have the same measurements for their angles. So that does create a set of similar triangles. Next one. Two of the angles of triangle ABC have the same measures as two of the angles of triangle DEF. Now, before we even keep reading, don't we just need the two sets of angles to get similar triangles? Yeah, so far, these two triangles are similar. Again, just like the last problem though, we need to make sure that the side lengths are not the same, because if the side lengths are the same also, then we don't have similar triangles, we have congruent ones. So what's the rest of the sentence say? And all of the corresponding side lengths of the two triangles are different. Good. We've got angle, angle. As long as two angles match up, that means the third one does. And if all three angles match up, then you have similar triangles. Next one. Triangle TUV is rotated 180 degrees clockwise about the origin and translated 3 units up to create triangle T prime, U prime, V prime. Did you see a dilation in there? No, I didn't either, which means that we don't have a similar triangle to the original. We have a congruent triangle to the original. You're only going to get a similar triangle through a transformation if one of those transformations that you do is a dilation. There's no dilation in here making the triangle bigger or smaller, so it's just going to be the exact same size as it was before, which means it'll be congruent. So we do not want to select this one because we don't want congruent triangles. Lastly, the 3 side lengths of triangle JKL are the same as the 3 corresponding side lengths of XYZ. I'm just going to stop right there. That's a congruent triangle. I don't need any other information. If the 3 side lengths of one triangle are the same as the 3 side lengths of another triangle, those 2 triangles are congruent. That's the end of it. They will absolutely also have the same angle measures. There's no way around it. This is going to make a congruent triangle. Sure enough, it says, and one of the angles of triangle JKL has the same measure. Well, not just one of them. All of them are going to have the same measure. So don't want to select this one either. Let's do one more. Which triangle is similar to the one above? Again, just like before, we have to figure out what our missing angle is to do this problem. Again, all 3 angles have to add up to 180. It will always be that way. How much do the 3 angles have to add up to? 180. You've got to get that stuck in your head. 3 angles in a triangle add up to 180. So here we go. We've got 122 plus 22. That gets us to 144. So how much am you missing? 180 minus 144 will get you to your answer, your 36. So we've got 122, 22, and 36. So if we can match up 2 of those angles with 2 angles in another triangle, we'll get it. So which one of these triangles has 2 of the 122, 22, and 36? We need to match up 2 of them. W, no. 72 and 20, neither one of those are in our yellow triangle. So that's wrong. 44 and 36, no. Neither one of those are in our yellow triangle. 50 and 72, no. Neither one of those are in our yellow triangle. Finally, 36 and 22, there it is. We've got our 22. And we got our 36 that we just found this other angle has to be. So it's triangle Z. All right. That's it. So main things to take away. You need 2 pairs of corresponding angles that are congruent to prove that 2 triangles are similar. And 3 angles in any triangle have to add up to 180 degrees. Those are the 2 main things. Your parallel line stuff you'll play with a little bit also. But work hard and good luck.